The first thing you need to learn is about Aubernais traits. It is a set of three elements which have similar chemical properties. They
Hmm.
are called triads. And usually the atomic mass of the central atom will be the average of the first and last. That is the important point here. For example, chlorine and iodines, the average value will be bromine, which will be close to 80.
हाँ.
Which you could notice from the values itself, 35.5, 127. Average comes to be around 81.2. Similarly, lithium and potassium, and the average comes to be 23, which is sodium. Calcium and barium, strontium comes to be the average around 88.5. The actual value is around 87.6.
Hmm.
The other traits which fit in that relationship includes this one: potassium, rubidium, cesium, phosphorus, arsenic, antimony, sulfur, selenium, tellurium, hydrogen, fluorine, chlorine, scandium, yttrium, lanthanum. Okay. This I would
Yes.
suggest you write and learn only the sets, okay, which are the important sets that you need to know. Correct?
Okay.
Chlorine, bromine, iodine, एक set. Calcium,
हाँ.
strontium, barium, एक set. Lithium, sodium, potassium, एक set. Correct? Like that, you should know the set. Another set which I forgot to write is iron, cobalt, nickel. This is another set as well. Okay.
Hmm.
So notice these sets quickly.
Yeah. एक सेकंड ना.
Hmm?
अब मैं ये शीट लेके आया इसका ट्यूटोरियल का.
Done?
So 1 second.
हाँ. Newland octaves, what thing you need to learn is that it is valid from lithium till calcium only. Okay. This will go with
Yeah.
the idea that after every seventh element, the eighth element will have a repeated nature of that particular first element. Okay.
Yeah.
And this goes pretty well for the first two, three groups. After
Hmm.
that, it is becoming difficult to figure out. Okay. So
Yeah.
you can see this is only valid up to calcium. No inert gases included, no d block elements included in this. Okay. Next one includes Lothar-Meyer curve. Correct. In Lothar-Meyer curve, we check out the average, atomic volume versus the atomic mass.
Hmm.
So as the atomic mass increases, how is the atomic volume changing? If you can notice, from lithium to carbon it decreases, for sodium it increases, and again for potassium it increases, and it goes like this, and for rubidium it increases. So from here we get a pattern. The pattern is that the group 1 elements, if you notice, always occupies the peak spaces. Okay.
Hmm.
And just before the group 1 elements, we will notice that we will have uh, elements from group 17, that too at a much lower value. They will not be at a higher value, at a lower value. And then just below the peak of the elements, you will have group 2 elements. You can see strontium, calcium, magnesium. Here you will have beryllium. Okay.
Hmm.
And D block elements usually have a similar atomic volume, most of them. So you can notice that in this space they will have very, very similar amount of atomic volume cases. Okay.
Okay.
So what we can say from here is that the most electronegative, electropositive elements like lithium towards cesium, they occupy the peak values.
Hmm.
And around the descending positions, you will have group 2. Halogens occupy ascending positions. Metalloid occupy bottom of the curve, just at the bottom of the curve. Got it? So the problem here is even though there is some pattern, it is very difficult to remember them. So there is no easy way out for Lothar-Meyer curve. Okay. Next, physical properties of elements are the periodic functions of their atomic weight. This was the basis of Mendeleev's periodic table. Okay.
Hmm.
So according to Mendeleev periodic table, physical and chemical properties are the periodic functions of their atomic weights. 63 elements was known. Inert gas were unknown. They were arranged in
Hmm.
vertical and horizontal rows and columns. So you can see there are 7 periods, which we call it as rows, and there are 8 columns as per Mendeleev's periodic table.
Hmm.
Within each group or a column, you had a subgroup A and B. Elements
Yeah.
in A, they are called normal elements. Element in B, they are called transition elements. Okay.
Yes.
Eka aluminium, which means gallium. Eka boron, which means scandium. Eka silicon, which means germanium. Eka magnesium, which means technetium. Okay.
Hmm.
These were then undiscovered. Later on, it will added. Okay. Because they belong to the B family, or I would say they belong to the same group. So they were named after the nearest elements. Clear?
Hmm.
These 4 names you must remember. Okay. Eka aluminium, Eka boron, Eka silicon, and Eka magnesium.
Hmm.
Eka manganese, sorry. Next, atomic weight is equal to valency into equivalent weight. This we know that. And the corrections in the atomic weight were done to the nearest integer values using this Mendeleev's periodic table. So that includes uranium, beryllium, indium, gold, platinum. For these elements, we Mendeleevs were able to find out the actual valency and make the correction in the atomic weights. Got it?
Hmm.
Next. Atomic weight which violates the Mendeleev's arrangement includes potassium and argon. As per as per as per the atomic weights, argon should have been much more than potassium, which is not the case. Correct, isn't it? Sorry, argon should have been less than potassium, which is not the case. Similarly, tellurium should have been more than that of iodine. Correct. So, and same way, cobalt and nickel, if you notice, nickel should have been more than cobalt, but that is not the case. Here also, thorium and what do you say? What do you call it? Rhizodonium. Okay. So these two,
Yeah.
if you compare, thorium would has more. Clear. So these are some certain violations which Mendeleev periodic table has been identified. Correct. See,
Hmm.
modern periodic table was derived out of Moseley's work, where he exposed atomic atoms under high intensity rays. Okay, and these rays, as they fall onto the metal surfaces, they will eject out the electrons from the inner shells in the form of X-rays. Correct. So these X-rays which are been coming out will be of a different wavelengths, but they all will be within the range of X-rays only. Okay.
Hmm.
You will see gamma 1, gamma 2, gamma 3. These are all the frequencies of those particular X-rays. Okay. So you can see wavelength of the X-rays decreases on moving from lighter to heavier elements.
Hmm.
See the mathematical expression root of nu, which is root of frequency is equal to A into Z minus B. Okay. So root of frequency is proportional to Z, which means more the atomic number, more is the frequency of radiation of X-rays. Okay, and he
Hmm.
used this logic to plot root of psi versus z, and he found that there is a very nice pattern of most of the elements that has been identified. Okay,
Hmm.
that's why he thought the property of elements can be more related with their atomic numbers and not their atomic masses. Correct? So you
Ah.
can see increasing order of their atomic numbers having similar property repeated after every regular interval. Okay, so that became his basis.
Yeah.
Clear? Next, he found that there can be nine vertical columns. 1 to 8 are elements which are regular ones, and another one which is zero group element. Inert gas were introduced by Ramsay. There are seven horizontal rows, which we call it as periods. There is not much change in terms of periods, as much as the Mendeleev periodic table is concerned, or whether it is Moseley's table. Clear?
Yeah.
These two are same. Next, you do understand what is principal quantum number, what is azimuthal quantum number, what is Aufbau's rule. So I'm sure you know these terms, right?
Yeah.
I don't think we need to go through this again. Yeah, Hunt's rule and all, right? How do we write that? Clear?
Hmm.
Now, notice this long form periodic table, which was finally, I mean, it is using the concept of Moseley's. It was completely given out by Bohr, Bury, Rang, and Warner. Clear? So
Ah.
seven periods, but 18 groups. Clear?
Ah.
So seven periods, but 18 groups in total. Hmm? Okay.
Hmm.
So
Yes.
A are called representative elements, B are transition elements. Clear?
Yes.
So you can see 1A to 18A, I mean 8A. These are the total number of uh, groups we have. So we have 1, 2, 3, 4, 5, 6, 7. After 7, 8, 9, 10, groups are being clubbed and they are called as 8B. Then we have 1B onwards up to 1B, 2B. Then we have 3A till 7A. Okay, clear beta? Right. So these are the ones which we had. Next, you can see number of periods if you compare, right? Within the periods, we will need to check out subshells, number of elements, and names. Okay. See, total we have seven periods. What about the subshell? You can see one is, then we have in second period we have 2s 2p, 3s 3p,
Hmm.
4s 3d 4p, 5s will have 5s 4d 5p. Okay, 6s 4f 5d 6p. Clear? Like that, these are
Ah.
all the subshells which we have. Okay, and now you see
Yes.
number of
Ah.
elements which are present in this particular periods include 2, 8, 8, then 18, 18, 32, and last one is incomplete, which is around 26.
Hmm.
Okay,
Yes.
right. So now notice if it comes to elements, we will have you know hydrogen and helium. These are the two elements we had, and that is the shortest period which we have. Okay, then
Yeah.
lithium to neon, that is another short element, short period. Sodium to argon will have same. Potassium to krypton will have slightly longer. Rubidium to xenon will be longer. Then you see cesium to radon, that is the longest of all. Okay, so that will
Hmm.
have 32 elements in total.
Yeah.
So I guess this part is clear, but this will be around 32
Yes.
elements. Right. So you can quickly go through it once. What are all the group 1, group 2? You can see 1A, 2B, 3A, 3B, 4B, and so on. The blue ones, these are all D block elements. These are all P block elements. The yellow ones, these are all S block elements. And this gray one, these are all F block elements. Okay, so just go through it once quickly.
Yeah.
Next, check it out. Classification of periodic table. It is based on block SPDF. Okay, S, that is the last electron is entering into S orbital.
Yeah.
General configuration is NS1 to 2 for it, and N could be anywhere from 1 to 7. That means 1s, 2s, 3s, like that. It could be up to 7. Two groups, 1A and 2A. These are the two groups which it has. One is alkali metals and the other one is alkaline earth metals. Group 1 has francium, group 2 has radium. Both of them are radioactive elements.
Hmm.
And group 1 elements include these, group 2 elements include these two. Okay, group 2 here.
Hmm.
Clear?
Yeah.
Next, P block. P block, last electron is entering into P orbital. General configuration is important to understand. Ns2, Np1 to 6. And N can vary from 2 to 6. Hmm?
Yeah.
So 6 groups from 3A to 8A. 8A is also called as the zero group. And you see metals, non-metals and metalloids, all of them are present in it. Okay. Group 13, if you notice, boron, aluminum, gallium, indium, thallium. These are the elements
Yeah.
which we have. Got it? And we call it
Yes.
as a boron family. Group 14 starts from carbon, ends with, lead, which we call
Lead.
it as crystalloid family.
Yes.
And see, this is niobium. Okay. This is the configuration, flavorium. Clear?
Hmm.
And these are livermorium. Correct? These elements are the last ones. Got it? Which I gave you the
Hmm.
list at the very, very early one. If you have noticed that, you can see this part here. Here. Got it?
Yeah.
Okay. Meitnerium, hassium, borium, seborgium, dubnium, rutherfordium. These are from 104 onwards. Got it? And here, if you notice here, sorry, clear? These elements which you have it right after this, those are the new ones which I have written in there. Clear?
Hmm. Yeah.
Next, see, these are the group elements if you compare. Group 15 has nitrogen to bismuth. Group 16 has oxygen to polonium, fluorine to uh, astatine, and group 18 is helium to radon. Okay.
Hmm.
The last element is Og. Good. That is the element which is present, which is 118. Clear it up? So that completes the table.
Yeah.
D block elements, the last element enters into d orbital here. You see the general configuration is ns1 to 2, n minus 1d, 1 to 10. D block, we have 10 groups. Okay.
Hmm.
Third B, next we have eighth B, then we have 1b to 2b. These are the elements which we have. Okay.
Yeah.
Here all the elements are metals except zinc, cadmium, mercury. Correct. These are non-transitional. Rest all are transitional elements. Okay.
Hmm.
Transition means they must have a different valency. Okay. Yeah.
Yeah.
Next. Next, you see these are categorized as series of elements. That is starting from scandium to zinc, which we call it as 3D group elements. Then yttrium to cadmium, which we call it as 4D group elements.
Hmm.
Lanthanum to mercury, which is 5D. Actinium to rutherfordium, that is about 6D.
Yeah.
Clear?
Yes.
Right. Next, you see, all the elements are placed within third group. Okay. Two series of elements are present, lanthanides and actinoids. So that includes lanthanide 57, cerium is 58, and actinium is around 71. Actinides, if you notice that from actinides towards lawrencium. So first it will
Hmm.
be actinoid element, then it is thorium towards lawrencium. Here it is cerium towards lawrencium. Lutetium, sorry. Lu means lutetium. Okay.
Hmm.
See, both lanthanides and actinoids are found in low abundance, right? So rare earth metals or the inner transition elements is what we call it. Next, all actinoids are radioactive elements. Elements after uranium, they are generally called as trans-uranium elements. Okay. Now, there are few terms which we need to know. First one is a diagonal relationship. Second period and third period elements which are diagonally aligned with each other, they will have similar properties. Okay.
Hmm.
And those are called diagonal, I mean, those are the ones which we have diagonal relationship. Okay.
Yes.
Next, ionic potential is equal to charge by radius. Okay. Usually, whenever we have to discuss ionic potential, we need to check charge by radius. So you notice this lithium, magnesium, beryllium, aluminum, boron, silicon, and carbon, phosphorus. Up to this, the relationships holds better, but thereafter, as it comes close, I mean, after carbon, nitrogen, oxygen, the relationship does not hold good. Okay.
Hmm.
Next, typical elements. Third period elements, except the inert gas elements, they are called typical elements. They represent properties of the other elements of the respective groups. Correct. So these are all the typical elements. Representative elements. All S and P elements which have incomplete octet are called representative elements. Remember, D and F को नहीं कहते, only S and P. Okay.
Hmm.
See, man-made elements. The first man-made element is technetium. Man-made lanthanide is PM. Okay, praseodymium.
Hmm.
Clear, beta?
Yes.
Next, metal, non-metal, and metalloids. If we compare, most of the elements are metals in periodic table. Usually, they are solid at room temperature. They have high boiling point and melting point, except for gallium, mercury. Metals are high electrical heat and electrical conducting uh, elements. Then metals are malleable and ductile also.
Hmm.
Okay,
Yes, sir.
non-metals. You see, usually, usually they are solids and gases. They have low boiling point and melting point. They are brittle, less malleable, and ductile in nature. Metalloids, they have the property of both metals and non-metals. This is the list. So इनमें से अगर आप पूछोगे ज़्यादा important list, that is about metalloids बेटा. You got to know what are the metalloid elements. Okay,
Yeah.
so please check it out once. Clear?
Yeah.
Next, IUPAC nomenclature greater than 100. Root name. What is the root name? So 0 to 9, what do we have? Nil, un, bi, tri, quad, pent, hex, sept,
Also.
oct,
Oh.
n.
Yeah.
Okay.
Yes.
Next, everything suffix must end with em, ium. Got it?
Yes. Yes, sir.
So based on that, these are the names. Okay. You got to understand these terms as well. What is the official name for all of them?
Yeah.
Okay. So you can see Mendelium, Nobelium, Lawrencium, Rutherfordium, Dubnium, Sevorgium, Borium, Hassium, Metnium, okay, Dermastadium. Clear?
Yeah. Yes.
Next, parameters which have trend over the periodic table. First one, effective nuclear charge. Okay. Valence electrons
Yeah.
experience lesser attraction from nucleus due to intervening of inner electrons. So nucleus is generally shielded by inner electrons. The shielding of nucleus by inner electrons and is that what we call it as shielding effect. You
Yes.
see, net charge valence electrons gets attracted is called ENC, effective nuclear charge, which is equal to Z minus sigma. Z is the
Yeah.
total nuclear charge, and sigma is the shielding factor or shielding constant.
Huh.
As per Slater's rule, every NS-NP electron contributes a factor of around 0.35. Okay,
Yes.
if the last electron is in nth orbit and if it has ns and np electrons in it, okay, more other than the
Yeah.
valence one, or भी ज़्यादा है, so then those will be contributing around 0.35 to the screening factor. Next, each n minus 1 shell electron contributes to a factor of 0.85, and
Yeah.
each n minus 2 shell and inner shell contributes to a factor of 1.
Yes. Okay.
Sorry, check out. On one is the screening factor due to other elements is only zero point 0.3. Matlab, within the first orbit, if you notice, this one and this one, between these two only, the screening factor is 1. Okay.
Yeah.
Next, you can notice this part here. Iron, what is the configuration? If you have n minus 2, n minus 1, and n. And see, if this is a reference element, correct? So then
Hmm.
this would be nth orbit electrons. This would be n minus 1. This will be n minus 2. Okay,
Yeah.
बेटा. तो यहाँ से चेक कर लो सिग्मा कितना कंट्रीब्यूट कर रहा है. Adding all the values, you'll get 22.25. So Z effective of 4s1 electron is 3.75. That is how you need to check it.
Yeah.
Now down the group. Check out down the group what is happening. Lithium, if you calculate, you're getting 1.3. And lithium, in fact, group 2 period, second period elements are exceptions. Unke Z, they will get the Z effective value, which does not follow a pattern. But if you notice, sodium, potassium, rubidium, they all are following a pattern. When you
Hmm.
calculate their Z effective value comes out to be same. Okay. And this
Yeah.
becomes an important way to explain why the size is increasing down the group. So as you go down the group, the number of orbits are increasing, but the Z effective remains same. And because Z effective is same, they all will have uh, they all have been added new orbits. So what should happen? The size will increase.
Huh.
Okay.
Yeah.
Next notice. Down the group, Z effective remains almost same for all the elements. Since electrons are added to the new shells, size of the atom increases.
Hmm.
Next, check out from left to right. Check out beryllium 4, 1s2, 2s1, and 2s1. Okay,
Hmm.
1 into 0.35 plus 2 into 0.5. So that total is 2.05. So Z effective is 1.95.
Hmm.
Boron, if you have 2p1 and then rest of the electrons here, see, your contribution is 2.6. So here you can see one pattern. Left to right, the Z effect is only increasing. 1.95, 2.6, and it will keep on increasing. Clear?
Yes.
Mm. So I got left to right, Z effect increases since electrons are added to the same shell. Atomic size decreases.
Yeah.
So I got lithium towards fluorine, the size will decrease here.
Hmm.
Okay. Mm. And then if it is down the group, you can see size is increasing here in all the cases. Now, there are
Yeah.
always four types of radius that we need to understand. One is covalent radius, which is one half of the distance between the two nucleus when they are covalently bonded. So when two atoms are covalently bonded ना बेटा, उनमें जो distance होगा उसका half हो जाएगा covalent radius. Okay, so you can
Yeah.
see chlorine has a internuclear distance of 198. So that is half of that is 99. Okay,
Hmm.
next. Heterodiatomic cases, if you notice, d of AB is equal to A plus B, correct? If electronegativity is same. If electronegativity is different, then you have to you have to subtract this factor minus 0.09 into difference in electronegativity. This is called Stevenson-Shoemaker formula. Got it? Clear?
Yeah.
Radius are all in Armstrong units, and psi is equal to Pauling scale. Okay, clear it up.
Yeah. Yes.
So check it out. What will happen to the distance? Radius of x is given. Radius of c, correct, is you can calculate that. Thereafter, distance between c and x will be equal to minus 0.5 plus 0.77 minus 0.09 into 1. Okay, so which is equal to 1.18.
Yes. Okay.
Next, metallic radius. Atom which are closely packed in the metallic crystal, that is called the metallic radius. See, आप ऐसे समझ लो कि atomic nuclear so usually here we will have the overlapping radius when it comes to covalent character, but in ionic radius they will be touching each other like this.
Yeah.
So you can see internuclear distance is this long here, and radius of the crystal is equal to radius of the metal, which is equal to half of internuclear distance. Clear? Next,
Hmm.
van der Waals radius is between the two molecules, and the radius existing between them is called van der Waals radius, which is equal to intermolecular forces of attraction by 2. We have got the chlorine. In non-metals, when the atoms or molecules come close to each other in solid state, the atoms or molecules have certain defined internuclear distance. Now, usually किसी भी molecule का van der Waals metallic and covalent radius compare करोगे, so this is how it will vary.
हाँ.
ये बेटा देखो हाइड्रोजन टू क्लोरीन में चेक करो कोवेलेंट रेडियस एंड वैन डर वाल्स रेडियस हाउ डज इट वेरी यू कैन सी द वैल्यूज वंस
Hmm.
क्लियर है
Yes.
नाउ कंपेयर फ्रॉम लेफ्ट टू राइट डाउट
Hmm. Yeah.
नेक्स्ट shielding effect by subshells, so you can see ns np nd nf this will have more shielding effect. This is due to penetrating power. Ability to come closer to the nucleus is called as the penetrating power, out of which Ns, Np, Nd, Nf, this is the order which we will have.
Yeah.
Next, as the Z effective increases, the cationic and Z effective uh, cationic values, if you notice, what would happen? Z effective increases, the cationic size will decrease. If Z effective decreases, what happens to the anion beta? If Z effective is decreasing, Z effective is increasing, decreasing means as the anion increases, it's better.
Hmm.
Clear? Check.
Yeah.
Z effective wise, if you notice, charge wise, if we compare, always the higher, even positive charge will always be uh, smaller compared to that of sodium compared to that of Na minus. Finished?
Yeah.
Check out group 13 once quickly.
Hmm.
Push clear beta.
Yes, 1 second. Yes. No.
Next, notice atomic size in D and F block elements. How does it vary? From scandium to zinc, first it will decrease up to chromium, then slightly increase to manganese, then decrease. Again, from copper to zinc, slightly increases. Now, why does that happen? As the Z effective increases, you can see. Finished?
Yes.
These are few exceptions from group 30 D block elements. Please go through it once. Dekho. When it comes to zirconium and hafnium, niobium and tantalum, molybdenum and tungsten, they all will have similar radius because electrons are entering into F shell. And when electrons are entering,
Yes.
clear?
Yeah.
Next. Ionization potential check करो.
Yeah.
Done beta. Check out ionization.
Yes. Yes, sir.
Right. See, first element removal if the energy is E1. The second element removal will be always much higher than E1. चाहे वो कोई भी element हो, it will always be higher in the first one. Okay.
हाँ.
Alright. So you can see size of the atom decreases every time an electron is removed in the size.
Yes.
Finished?
Yeah.
Check out quickly the what are the factors that influence the ionization energy. Please check.
Hmm.
Yeah.
Yes.
Please let me know if you didn't understand it.
Yes, once again.
Oh
Yes,
yeah.
man.
Right. Now, usually check out the trend from left to right and down the group. How does it vary? And where is that problem? I mean, where is the variation coming? Please check.
Yeah. Yes, man.
Right. Next. This is the typical application of ionization energy. Just read it once quickly.
Yeah. Yes.
Right. Next. Check out the referential things. That means group 13, how does it vary? Group 14, how does it vary? Because यहाँ पे variation है ionization का.
Yeah.
Okay. So वो पता होना चाहिए. Hmm? Yeah.
Yes, sir.
Next. Metallic or electropositive nature. Notice that. Hmm. Okay.
हाँ. Yes, sir.
See the reducing power here. It is a similar trend as that of electropositive character. Ionization 1, 2, 3, and up to 6. If these are the values given, correct?
Hmm.
Then how do we know that which element does it belong to? Okay. Generally, 200 to 400 रहेगा तो group 1 and 2, and 1400 to 3000 रहेगा तो group 16, 17 के बीच में रहेगा. Okay.
Yeah.
So which means here the element given looks like more of group 17. No?
Yes.
So based on that you can see first ionization, second ionization का variation कैसे होगा. Okay,
Hmm.
check. हो गया?
Hmm. Yeah.
Then D block elements.
Yes.
Next, check out in 3D series what is the first ionization, second ionization, third ionization, highest values and lowest values. But इतना ही पता होना चाहिए highest और lowest क्या आता
Yeah.
है. Down the group check करो.
हाँ.
Next, notice now electron affinity. Hmm?
Hmm.
Electron affinity is energy released when electron has been added to X. Correct?
Hmm. Yeah.
See, when it comes to successive electron affinity, that means adding one electron, then adding one more electron will always give you negative energy. It is not a release energy.
Yeah.
Right. Next, see what are the factors that influence the activation energy. Quickly check off all 4 points.
Yeah. 1 second.
Ah, finished.
Yes, sir.
ये important list है, that is elements which have negative electron affinity. Okay, so you can see
Yes.
beryllium, magnesium, nitrogen, and all the inert gas elements. Only these are the elements which will have negative electron gain enthalpy.
Yeah.
Next, finished.
Yeah.
Check out down the group. How does it vary? Electron affinity.
Yes, sir.
Yeah. Now, generally, third period elements has more electron affinity than the second period elements of the respective groups. Okay.
Yeah.
So usually this is the order you need to understand if you have to compare the second period and third period elements. Okay.
Hmm.
Next, notice electronegativity. Electronegativity wise, I mean differences आपको पता ही है what exactly they are. Just go through the Pauling scale once. What are the values you have? जस्ट वैल्यूज को चेक करो बस क्विकली. Yeah.
Yes.
Check out the scales and their values beta quickly. Mulliken scale क्या है, Alfred Rocho scale क्या है, Pauling scale how it is been defined. Okay.
Yeah.
Yeah. So how do we find the electronegativity difference using Pauling scale, Mulliken scale, Alfred Rocho scale?
Yes, sir.
Done?
Yeah.
Yeah. Now you notice what are the applications of electronegativity. Generally, bond energy, bond angle, bond energy. These are the applications of electronegativity. Okay. Check out in the first case bond strength. So this is higher bond energy than this, than this, than this. This is because of difference in the electronegativity.
Yeah.
So you can see more the S character, stronger is the bond energy.
Yes, sir. Yeah.
Done?
Yes.
Next, see more S character, stronger is the bond energy here. Okay. And you can see X, Y, Z. You can compare that easily. Okay. Which one has more bond energy or not? Hmm?
Yes.
Nice. See, mathematically, DAB, that means distance between AB, can be used by this formula. And you see, covalent radius of this is given. Calculate the electronegativity of Alfred Rocho scale. ये एक important question है, check कर लो एक बार. Covalent radius दिया है तो कैसे solve करना चाहिए. I'll discuss completely uh, about how to solve the Alfred Rocho scale. Please check करो एक बार सारे values को.
हाँ.
समझ में आया?
Yes. Yes.
हो गया?
Yeah.
Check out how to figure out the percentage ionic character. ये फॉर्मूला है, इसको कहते हैं हैनिश स्मिथ फॉर्मूला. यूज इट एज Hannay and Smith formula. Directly you can use this formula, figure out how much is the percentage ionic character. Got it?
Yeah.
Next, if you have to calculate the distance formula DHF, देखो unit conversions ध्यान से देखो what we are using. Armstrong units को ही use करना चाहिए इस case में. That's how you can get the distance. कभी कभी picometer में दिया होगा, so just you need to change that. Finished?
Yeah.
Next, more the positive charge, more is the electronegativity, and same way, more negative charge, more is the less is the electronegativity. So these are the factors you need to understand as it comes to more positive or negative charge here. Okay.
Section number 2 question number.
Out. Quickly go through the exceptions of electronegativity group wise. Group 13 से 17 check करो एक बार.
हाँ.
हो गया?
1 second. Yeah. Yes, sir.
Finished? If you
Yes, sir.
notice from left to right, how does the acidic strength varies? Correct. And down the group, how does it vary? Down the group, you need to check only about the bond dissociation energy, beta.
Yeah.
इलेक्ट्रोनेगेटिविटी डिफरेंस को कंसिडर नहीं करना चाहिए डाउन द ग्रुप.
Yes.
Check out nature of oxides. Which of them are basic, which of them are amphoteric, and which of them are acidic.
Yeah.
Neutral oxides. Check here.
Yes.
Next, check out. As the electronegativity of the central atom increases, acidity increases.
Yes, sir.
Finished, right? Mm. Check out lattice energy beta. The amount of energy released when 1 mole of cation and anion combine to form 1 mole of solid crystal. So like this,
Hmm.
if these two are combining, the energy released is called lattice energy. So it depends upon, you know, inversely proportional to radius and directly proportional to charges.
Yeah.
What are the factors that influence lattice energy? One is intermolecular distance, the other one is charge. Higher the charge, higher will be the lattice energy.
Hmm. Yes, sir.
Next, next. So about hydration energy. This is the energy released when a cation will convert into an, any ion will convert into an aqueous ion. That is called hydration energy.
Hmm. Yes, sir.
Hmm. Reducing and oxidizing power. Please check this case once. ये आ जाता है usually exam में पूछने को. So please check this.
Yeah.